Hello students, so in the previous class we started with differential equation of higher order. So up until that we had mostly first order ODEs, of course nonlinear type, and then we looked into existence, uniqueness, and then stability, chaotic behavior and all that. Now we are looking into differential equation of higher order, and in the previous class we introduced the concept of linear independence and dependence, and how to check with the help of Wronskian, and also if we know one of the solutions, then how to guess the other solution or how to get the other solution. Those methods we have seen. Now in today's class we'll start with linear differential equation of higher order, right? So it can be homogeneous, non-homogeneous, doesn't matter, but with constant coefficients. So up until whatever we had d square y by dx square and all that, you may have d3y by dx cube or d4y by dx4 and so on. So I mean basically a linear differential equation, but of involving higher order derivative terms, and simultaneously it can have right hand side 0 or non-zero, right? So just to start with, or give you one example. So suppose we have, let me take an easier example. So suppose we have something like this, d, 1 minute. So we have, let's say, d4, d4y by dx4 plus 5 d3y by dx cube plus, let's say, 6 d square y by dx square plus, I don't know, 3 dy dx plus y equals to, either we have 0 or we can have some function of x, which can be, I don't know, you can take or it can be given e to the power x, log x, sin x, and whatever it is. I mean, there is a way to calculate particular integral based on the given function, but as far as this type of equations are concerned, we can have higher order as well. So in general, if it is of higher order, then the way to solve them, if suppose if the right hand side is 0, then in that case basically we say that let y is equals to e to the power mx be the trial solution, so solution, and then since if it is a solution, then it must satisfy this equation. Let's call it as equation number 1. So if it satisfies this equation, then in that case we'll have e to the power mx, and then we'll have m to the power 4 plus 5 m cube plus 6 m square plus 3 m plus 1 equals to 0. Remind you that this is an hypothetical example, so I am not sure whether I can be able to factor this out and get all the real roots or imaginary roots and all that. One has to solve, right? But the working principle is what I am going to explain. So obviously you have product of two quantities equals to 0, but e to the power mx is non-zero all the time. So exponential function is, as long as x is not tending to infinity and m is not negative and all that. So in general you can say that e to the power mx is non-zero, so this factor must be 0, and therefore from here we can solve for m. So obviously you will get 4 roots. Let us say it is possible to solve this, and we got 4 roots, lambda 1, lambda 2, lambda 3 and lambda 4. Now based on the fact that if all of them are distinct and real, so then in that case the solution will become, so first case is lambda 1, lambda 2, lambda 3 and lambda 4 are all real, and distinct. So then in that case the solution yx will be given by c1 e to the power lambda 1 x plus c2 e to the power lambda 2 x plus c3 e to the power lambda 3 x plus c4 e to the power lambda 4 x, right? If all of them are distinct. Now it may be possible that 2 roots are same or 3 roots are same or all 4 of them are same. So, depending upon how many roots are same, this solution will change, right. So, the second case will be lambda 1 is equals to lambda 2 and lambda 3 and lambda 4 are distinct and lambda 4 are distinct. That means they are different. So, then you will have yx equals to c1 plus c2x into e to the power lambda 1x, or you can call lambda 1 equals to lambda 2 equals to lambda, and then we will have c3 e to the power lambda 3x and c4 e to the power lambda 4x. If three of them are equal, then you will have c1 plus c2x plus c3 x square into e to the power lambda x plus c4 e to the power lambda 4x, and if all four of them are equal or same, so then in that case we will have yx equals to c1 plus c2x plus c3 x square plus c4 x cube and then e to the power lambda x, right. So, depending upon how many of them are distinct, how many of them are different, you can write down the solution. Now, if any one of them, if two of them becomes complex, that means the complex roots occur in conjugate pair. So, lambda 1 will be conjugate of, let us say, lambda 2 and all. So, you can take lambda 1 equals to alpha plus I beta. So, other one will be alpha minus I beta, and then we can write. So, let us say lambda 1 is equals to alpha plus I beta and lambda 2 equals to alpha minus I beta, and lambda 3 and lambda 4 are real and say they are distinct. If they are same, then then this will happen, and for the lambda 1 lambda 2 you will have in terms of cos and sine. So, here in this case we will have yx equals to e to the power alpha x into c1 cos beta x plus c2 sin beta x plus, I am saying lambda 3 and lambda 4 are real and distinct. So, this will be c3 e to the power lambda 3x plus c4 e to the power lambda 4x. If all four of them are complex, then it will be e to the power alpha c1 cos beta x plus c2 sin beta x plus e to the power gamma x c3 cos delta x plus c4 sin delta x and so on. So, you got the idea, right. That is for the fourth order. If you have fifth order, sixth order and so on, so the analogy will be similar. So, in case all the roots are distinct, then you will just increase the power of that polynomial times e to the if all of them are same, then in that case you will just increase the order of the polynomial times e to the power lambda x. If all of them are distinct, then you will write c1 into e to the power lambda 1x, c2 e to the power lambda 2x and so on, cn e to the power lambda nx. And if any one of them are occurring in conjugate pair like complex numbers, so then you will take help of this representation, right. So, going from second order to higher order is pretty much same for constant coefficients, right. Now, the interesting part is when you have right hand side as a function of x. So, then how do we handle and what do we do? That is an important question here. So, suppose we are given dny by dxn plus p1 times dn minus 1 y by dxn minus 1, and this will continue up to p1 pn minus 1 dy dx plus pny is equals to some capital X. Let us call it as equation number 1. So, where capital X is called the input function, is called the input function, and the coefficients p1, p2 up to pn are constants, or they can be function of x also, but that we will look later on. So, for next two lectures I will devote for constant coefficients, then I will look variable coefficients. So, they can be constant or they can also be functions of x, or they can also, so that is why I am writing it in bracket, they can also be a function of x, not a, they can be functions of x, that can be possible, right, x only. So, the dependent variable and its derivative, it is appearing as dn y by dxn, dn minus 1 y by dxn minus 1 and so on, and independent variable is x here, right, and right hand side is a function of x, it can be a function of x. So, here in this case basically if x is 0, then we call it as homogeneous, as I am repeating this term again and again, and if x is non-zero, and if x is non-zero, then this will lead to non-homogeneous nth order differential equation with constant coefficients, right. Now, there is a little theorem here which I want to say. If y is equals to fx be a general solution of, okay, here I will introduce a notation so that I do not have to write this big expression. So, I will introduce a notation, let us call it as d, this symbol, d math BBD equals to x. Let us call it as equation number 2. So, this is the notation I am using for the left hand side. So, dn, where this dn is equals to dn by dxn plus p1 dn minus 1 by dxn minus 1 dotted up to pn minus 1 ddx plus pn whole bracket, and that is basically our capital Dn, and then when you are charging y, the y will be distributed to all the derivatives, right. That is a small notation that I am using just to avoid writing right. This is what I mean, Pn. So, this is my Dn. So, if y is equals to fx be a general solution of dn y is equals to 0 and y is equals to phi x be a solution of dn y is equals to capital X, then y is equals to fx plus phi x be a general solution of dn y is equals to capital X, right. This is also very easy to see, because we can substitute y is equals to fx plus phi x here. So, this is very straightforward. So, proof is very straightforward. We can have dn y is equals to dn of fx plus phi x, right, and this is dn f plus dn phi, but f is a solution of dn y equals to 0. So, that means this will become 0, and dn phi is a solution of this equation. So, this will become x. So, x. Therefore, this implies that y is equals to this modified fx plus phi x. You may want to call it as y cap, that is also fine. So, dn y cap. So, y cap is a solution of same equation, dn y is equals to capital X, right. So, this is the idea that will run behind when you have a non-homogeneous ordinary differential equation. So, we will determine the complementary function, then which is taking the right hand side as 0. That means, you work with the homogeneous equation and obtain the solution. So, that will be the complementary function for the given ODE, and then we obtain the particular integral and we add them, and we say that this is the complete solution or the general solution of your given ordinary differential equation, right. Now, next small theorem is theorem is if y is equals to y1, y is equals to y2 dot dot up to y is equals to yn be integrals or the solution be integrals of the equation dny is equals to 0, then y is equals to c1 y1 plus c2 y2 plus dot dot up to cn yn, where c1, c2, c3 up to cn are all constants, is also a solution or is also an integral, since I am using the term integral in this theorem, integral of the equation dny is equals to 0. Obviously, because if y1 and y2 are the solution, so you add them, then you do the dn of y1 plus y2 equals to dn y1 plus dn y2. But y1 and y2 are solutions, so dn y1 and dn y2, they will both be 0. So therefore, the addition is also a solution, right. So adding the two solutions, so you can take c1 and c2 arbitrary constant, they will just come out of the derivative. So basically c1 y1 plus c2 y2 is also a solution, you can go up to n and that will also be a solution. So it is very straightforward to see in this case that y, if y1 and y2 are the solution, then their linear combination will also be a solution. So this is pretty much obvious, I would say, or straightforward to see. Okay, so now we know at least two basic theorems. We can proceed further. I think I also mentioned that so every now and then I will use capital D as d dx, then capital D square as d square by dx square, then this will keep on going, and we will use capital Dn is equals to dn by dxn, whereas this bold dn is that linear combination. In a way, here you have p1 dn minus 1 by dx minus xn minus 1 dot dot up to pn minus 1 dy dx plus pn, right. So this dn and this dn are different, so do not get confused, these two dn's are not same, they are different. There is a difference in the notation as well. Okay. Now when we are having this dny, so next to obtain auxiliary equation or to be precise complementary function, to be precise complementary function for dny is equals to capital X, we take dny is equals to 0, and from here we can try to write dn which is equals to, let us say, a function of d's, because they are function of d's, which is dn plus p1 dn minus 1 plus dot dot up to pn as a factor in d, What does that mean? It means fd is equals to, we have dn plus p1 dn minus 1 dot dot up to d plus pn, and sorry, p1 pn minus 1 pn, So from here we can think of that by some way, using some factorization and all, we are able to write d minus m1, d minus m2 dot up to d minus mn. And therefore, to obtain the auxiliary equation, we say that we do that fd is equals to 0, and from here we will get d minus m1. So since this equals to 0, so from here we will have, so for auxiliary equation we will have f dy is equals to 0. So we will have d minus m1 y equals to 0. Since you have product of n factors as 0, so basically each one of them must be equal to 0. So d minus m2 y equals to 0 dot and so on, d minus mn y is equals to 0. So from here we will see whether m1 is equals to m2 or not. So then in that case, if all the mi's are distinct, so then we will write the solution as y is equals to c1 e to the power m1x plus c2 e to the power m2x and so on up to c n mn e to the power mnx. If any one of them are equal, then in that case the solution will change accordingly, and if it occurs in the complex conjugate form, then in that case the solution we can write will be of that e to the power alpha x and cos beta plus sin beta and all those forms, right. So from here we can write down the solution or the complementary function very easily. Okay, now comes the interesting part. So let us say this is the solution that we will obtain. Now case of unequal roots, equal roots and imaginary roots, that can also be discussed from here. So that means if all the mi's are different, so I am just going to write down, we can write the solution, if all mi's are different but real, just like before. Second is we can also write the solution if all the mi's, if not all mi's are different but they are all real, right. And third one is we can write the solution if some mi's or all of them are complex, right. So either it can be some, let us say m1 m2, or it can be all of them are complex, and then in that case we can write down the solution accordingly. Number of terms will definitely increase, yes, no doubt. And let us solve one example before we can move to the particular integral part. So if we solve, let me take one example of this type. So d4y by dx4 minus d3y by dx cube minus 9 d square y by dx square minus 11 dy dx minus 4y is equals to 0. So solution. Let y is equals to e to the power mx be the trial solution, then we will get m to the power 4 minus m cube minus 9m square minus 11m minus 4 equals to 0. Very straightforward, right. And from here we can try to solve this. This will become m as minus 1, minus 1, minus 1 and 4. Okay. So these are the 4 roots of this biquadratic equation. Therefore, the required roots, the required solution, the required general solution, we can write required general solution of the given ordinary differential equation is y is equals to, we have all three roots are same. So, c1 plus c2x plus c3x square e to the power minus of x plus c4 e to the power 4x, and this is the required solution of the given ordinary differential equation. So, if you know this how to write down the solution, then writing this expression is very easy, right, because it just if you remember for let us say 1 or 2, then in that case up to second degree, then you can generate up to any degree here, because it is just adding one more term and one higher degree. Okay. It can be also of this type. Example 2, let us say by some way we know that it is d square plus 1 whole cube, and then d square plus d plus 1 whole square equals to 0. So, that means here you will have d to the power 6, and here we have d to the power 4. So, at least a d to the power 10. So, that means it is a ordinary differential equation of order 10. So, there will be 10 independent solution for this equation, and we can just write down like this. Since right hand side is is 0, we can write the auxiliary equation. The auxiliary equation is m square plus 1 whole cube, and then m square plus m plus 1 whole square. So, from here if you solve, from here we can see clearly it is plus minus I plus minus I plus minus I, and another two roots are minus half plus minus I square root of 3 by 2, and then minus half plus minus I square root of 3. Hopefully it is correct. So, then we can write down the general solution. Therefore, the required general solution is y is equals to c1 plus c2x plus c3x square into cos x plus c1x plus c2x c3, that means c4x, c5x and c6x square into sin x. Then we have c1 plus c2x or c6, so c7 plus c8 c8 cos of root 3 by 2 x plus c9 plus c10 sin of square root of 3 by 2 x into e to the power minus of half x. So, this is the where c1, c2, c3 up to c10 are arbitrary solutions. So, this is the required general solution of the differential equation 10 of the 10th order ordinary differential equation, which is given here, right. And similarly, you can have more than power 10. I mean, you can have even 20 here. It's just that you must know how to solve that auxiliary equation and get the solution of m in real numbers, complex numbers, but at least some real number, in a way, right, or complex number. And then the general solution can be written just as before. We have generalized the definition of the solution what we mentioned before, right. So, this is the technique to solve the second order and higher order ordinary differential equation for homogeneous case. In the next class, we will look what happens when the right hand side is not homogeneous. That means right hand side is a function of x, and then we will define the operator FD in a little bit different way, and then we will try to find out the something called particular solution. So, I will stop here today, and I will continue this discussion in the next class.